So when it's more than zero, you see the spindle, but when the inhibitory neurons flash, you see the dead part.
No. That's a good question.
Because you're trying to, that state chart models the motif, right? Models the activity you see on the EEG.
That's
because
right.
When the
That's right.
Yeah.
Inhibition doesn't necessarily mean that you destroy the signal.
It means that the dy dx is negative, it goes down, right?
Yeah. I mean, it's the reason for this is not necessarily captured. I mean, you can have a region where you have flat EEG or flat local field potential. Right. This is associated, for example, I'll give you one example, one phenomenon. This is called AHP, after hyperpolarization. That is, it's a phenomenon that I haven't included in here. It means that for some times, the neurons will not be able to fire because it is hyperpolarized. And then during that period of time, the neuron cannot elicit any action potential because it went too far. And then there is a rebound, it takes time, and then the neuron can fire again.
Right, I'm just thinking, so if that model was true, right, what you will see on the EEG was basically you will see the spindle shape, but then it will eventually just become noise. So what we see on the EEG, where we see the spindle size being more or less consistent.
This model has nothing to do with flat EEG.
I'm thinking if that model was true, you wouldn't see any spindles, you would just see a dying signal.
No. I'll show you what you get. Okay. It's not intuitive.
Here, you mean by resource, it's just refractory period, right? It's not like a...
Refractory period, that's right. Which is not in here. Okay. What I'm saying is that you can define a region where you are, for example, not activating by a threshold, saying that if your activity is less than a threshold, you consider there is no activity. You can do this. What I'm saying, what I'm interested is that can you have something of the size of twice the size of this, 3 times the size of this noise?
Right,
can you have this?
Yeah,
where does it come from?
Yeah, you can, but how likely is it to happen, right?
Yeah, so that's right. So I'm going to show you that it happens all the time. It's not something that is a rare event. And so for this, let's go into the analysis of this equation. So how do you analyze 2D Ornstein-Ulembeck process? 2-dimensional Ornstein-Ulembeck processes. So we did 1, and now we go to 2 dimension. So the way I'm going to drive you in that direction, we're going to look at the distance to the origin. That is, if you have x and y, how do you look at the distance to the origin? You take the radius. You agree? That is the distance here, r of t, which is the distance to the origin. And I'm interested in what is the dynamics of this distance. So how do you calculate the dynamics of the distance r? You can say, I want to derive a stochastic equation, the same as here I have a stochastic equation. So how do I derive a stochastic equation for r squared, for example? Well, I need to have dr equals, so I will calculate dx and dy squared. So how do I do this? How do I calculate dxd of x squared? If you have studied the class of last time, you know. What shall I use? What shall I use? I need to use Ito calculus on which function? X squared is a function of x. So I have to use f of x equals x squared. And then I apply df for this function. So you remember df, what it is? Df of a process which satisfies this equation. You know, you remember it's ddf dx b plus 1/2 of ddf dx squared sigma squared dt plus df dx, and if I have it's sigma d omega. You remember this? This was the Ito calculus. All right, now I need to replace f by what it is, and b by this dynamical system. All right, so dx squared is what? The derivative of f is not hard, right? It's 2x, and the second derivative is 2. You agree? All right. Okay. So let's do it. And if I made a mistake, you let me know. df dx is going to be 2x multiplied by b by this guy, by x dot. So I have to multiply by b. So it's lambda x minus omega y. Great. This is 2x. That's it. Plus sigma. So sigma, so this is d. Square, sigma square. So this is 2d divided by 2. So it's just d. And the second derivative is 2. That's it. Plus sigma df dx. So this is square root of 2d. df dx is 2x. d omega 1. Is this correct? I think it is. And I do the same for dy squared. dy squared is 2y multiplied by omega x minus lambda y plus 2d plus 2d square root 2y d omega 2. And then I have to make the sum. All right, so this is dr squared. So 2x d and yeah, this is multiplied by dt, and this is dt. All right, 2x minus lambda. So here I have lambda. I have the factor 2. X squared plus y squared coming from here with a minus. So it's exactly r squared. I have 2x with a minus and 2x with a plus, so this is 0. So I'm left with 4xd plus y. I think this is... No, I made a mistake. There is no 2x here. This is just up to here, up to here. So there is no 2x. Because this is a second derivative, there is no 2 here. Right. Am I correct? So this is 4d, and this is delta t. And I have square root of 2d multiplied by 2, x dy1 plus y dy2. So how can I transform this? This is equivalent to what? To x squared plus y squared plus a new Brownian noise, d omega. You agree? This is equivalent to this plus 2 is the square root of 2d multiplied by 2 multiplied by this. That's delta t. Is everything equals? Do you agree about what I say? You understand what I'm saying? This is a Brownian motion. Brownian motion are characterized by what? By the mean and the variance, and that's it. The mean of this is 0, the mean of this is 0, the mean of this is 0. What is the variance of this? It's x squared plus y squared. What is the variance of this? It's exactly x squared plus y squared. So this is equivalent to this one, with a new Brownian motion that I define. Because they have the same mean and variance, so they are in law the same. Great. So x squared plus y squared, this is what? This is simply r. That's right. Great. So, yeah, so now Okay. And then I'll let you do at home. Now I'm interested not in r squared, but in r. So how am I going to go from r squared to r? I have to use, we did it once. You have to use again Ito calculus with which function? If I have a function f of r equal square root of r, I apply Ito to square root function, and this will give me dr. dr is going to give us d of f, which is square root of x squared, of r squared, which means r. You do at home. You see what I did here? So you know how to differentiate once and twice square root. So you do it at home, and you're going to find that dr equals minus lambda r plus sigma divided by r dt plus square root of 2 sigma d omega. Now this is quite interesting. This is your potential well minus v prime of r dt plus square root of 2 sigma dw. And what is v? V of r, so it is equal to lambda r squared divided by 2. If you integrate plus sigma divided by r, it's sigma log of r. So you have a potential well, and you have noise. What does it mean? You understand what I'm writing? D of r is a deterministic term, which is the gradient of this potential well. I just integrate plus noise. If I plot this, what do I get?
Depends about the noise. If the noise is too high,
I'm asking about the plotting of the potential well. What is this function? Maybe I can erase here. All right. So, as a function of r, this is v. So when r goes to 0, sigma log of r goes to, is this correct? Minus, no, I forgot, I made a mistake. There's a minus here because it's minus v prime, so it's minus minus, so it's plus, and plus and minus, it's minus. So when r goes to 0, this goes to plus infinity, and when it goes to plus infinity, so it's something like this, right? So there is an optimal position here with equal to what? When the derivative is 0, it's r equal, when r equals 0, lambda r should be equal to this, so r squared should be equal to sigma divided by lambda, so this is exactly this. Now you start to understand that the solution, okay, so now I need to, now we are going to use Fokker-Planck equation that you studied half an hour ago. I have a potential like this. What can I say about the distribution of the r? Where are located the radius? Well, I need a distribution. So how do I go for the distribution? I'm going to solve the Fokker-Planck equation associated to r. So what is the Fokker-Planck equation here? It's in your note. So the Fokker-Planck equation is what I just wrote half an hour ago. I need to solve, so I'm interested in the distribution. No, it's number 2. We're interested in distribution of the distance r of t. What are they? This is to answer Jean's comment. I'm interested in What exactly are we seeing? Are we seeing something small, or are there some more sophisticated behavior? Distribution of the distance R of t. So I'm looking at the probability density function, which satisfies the Fokker-Planck equation, which is dp dt equals sigma. So this is sigma squared divided by 2. So this is sigma ddp dr squared minus v prime of r dp dr. And yeah, let's go into the forward. It's ddr v prime p. And suppose I'm steady state. Suppose I study this and I'm waiting a long time, and I'm taking pictures of all of this, and then I'm asking, I project everything in R here. So this is the projection in R, and I'm asking, what are we seeing? Right? So again, this is the distribution of your EG. I'm now in dimension 2, and I'm interested in R, in the distances. So I'm asking, where is, if I take a picture, where is the process? So suppose you're at steady state. So this is 0, and I have to solve this equation. What do you get? Well, since you have a derivative in front of everybody, this is just dpr of sigma dpdr minus v prime of rp, and this has to be equal to 0. So if this is 0, that's, you get this equal to 0, and this is called the Boltzmann's equation. So p of r is given by a constant, and this is a first order ODE is sigma p prime minus v prime p. So you know this is p prime equals v prime divided by p. You integrate, so this is sigma log of p equals v plus a constant. So p, so I divide by sigma, and so what I get here, yeah, sorry, this is minus, I'm sorry, there is a plus here. Plus, so I go in the opposite direction, is p, so p of r equals exponential minus u of r divided by sigma with a constant. So it's exponential. So with a minus, so this is lambda r squared divided by 2 minus sigma log of sigma divided by sigma. And so if I divide, everything by sigma, sigma and sigma goes. Am I correct? This is with a minus, so this is with a minus, so there's a minus here and a plus here, which is equal to what? I think this is little calculation that are important to know, because this is how you understand things. It's sigma, so this is 1, exponential of log is r, and then you get exponential of minus lambda r squared divided by 2 sigma. And this is your probability distribution function. Well, this is interesting. Why is this interesting? Because from this, what do you see? What have we understood? What have we understood? Well, the distribution of the r, when r equals 0, this is 0. When r goes to infinity, this is 0. And we have somewhere a maximum. So there is a maximum for the distance of a process which is stochastic, but yet there is a distance here. So where is this maximum? The maximum, if you have to differentiate this, right? So if you differentiate this, this is exactly where you have your minimum. It's R0 equal sigma divided by lambda. So the position of your, if you take pictures of this, the distance, there is a distance here which is not 0, which means your process is not just in 2D, it's not just lying at 0, it lies at a certain distance, and the distance depends on the size of the noise. If there is no noise, there is not such a thing. So this is interesting, that this equation shows that in average, so having a big amplitude, something that goes very far away, is going to be exponentially small. Having something which is close to zero, it's also zero. So there is a maximum. And then there is more. There is more, and for this, I need to go to the same analysis that we did with the Lorentzian in dimension 2. So this is a little bit involved, but I need to show you this. So we have understood from this about the distance. And now we are interested, what are the frequencies? What are the frequencies of this? Well, if you have some intuition, what would you say? What are the frequencies in this oscillation? What your intuition is telling you? Let's go back to the dynamical system that was just written here. What was written? It was written that x dot equals minus lambda x plus omega y. Y dot equals minus omega x minus lambda x plus noise. So we said that in this is lambda is the rate at which you go exponentially to zero, but omega is your velocity, the angular velocity. If lambda equals zero, and if you just have omega, omega is your oscillatory regime, the oscillatory angle. So maybe we expect that this oscillation, because if it follows this and the noise is small, the oscillation is going to be around omega. So that's what we want to prove. The oscillation will be around omega, but we will see that there are more. And there is a continuum. There's a continuum because of the noise of frequencies. But yet, and we will see, it's called stochastic resonance. There will be a resonance at omega. Okay, so for this, we need to go through the same steps that we've been in dimension 1. In dimension 1, you remember how I showed to you what is the Lorentzian? We went to correlation function. We calculated the correlation function by integrating the process. And by integrating the process, we went to the power spectral density using Fourier. Right? So we should do the same. So then what you need is to start, so I can write this. So I'm not going to do all calculation, I'm going to show you how to calculate. So this is a matrix. I call this matrix A, so I have S, which is X and Y, and this will be written in a stochastic equation, X dot equals AS plus sigma omega dot, which means S is dimension 2, omega is omega 1, omega 2, A is this matrix, so it's minus lambda, omega, minus omega. You want me to write everything? A is minus lambda, omega, minus omega, minus lambda, and sigma is identity matrix with 2D. 2D, 0, 0, right? I mean, this is classical stuff. That's why I'm not spending too much time on this. That's how you write n-dimensional stochastic equation. And then what we need is, as we said, to calculate the correlation function Cx. X, so let me write it T and S, which is the expectation of the signal X of T, or let's say S of T. Yeah, okay. So here I already did the projection. All right. So I because there are 4 correlation functions now, or 3 really. You can correlate X with X. You can correlate X with Y, and Y of X is the same, and you can correlate x, y with y. So it's going to be, the correlation matrix. So I take the correlation matrix for the first one, which is, I'm going to take the projection only for x. So it's x of t minus the mean expectation of x of t minus, now multiply by x of s, multiplied by x of s minus expectation of x of s. Okay, the mean is 0, as we said before. And so what we are going to be interested in here is in the square term, the correlation term. Okay, so for this I use the same trick as before. I multiply by exponential a of t. I do the same as what I did in dimension 1. And you get s of t, the result, I'm not going to do the calculation, is s of t equals exponential ta of s0 plus integration from 0 to t of exponential of t minus s minus lambda sigma d omega s. And the same way I calculated ct of s, you have to take, I have to take the expectation of what, so let's take, because t will be large, I have to send t to infinity, so I don't care about this term. And then I have to do the same as I did before, it's expectation of integration from 0 to t of exponential minus t minus s sigma d omega s. And here what you need is to do the transposition. Yeah, so I have to, okay, it's integration from 0 to, yeah, if I put s is not great, so I put s1, integration from 0 to s, exponential minus lambda of t minus s2 sigma transpose d omega s2. And the same as before, this multiplied by this is going to give you a delta t only for s1 equals s2. And when you calculate this, and there is a sigma, yeah, okay, that's okay. So sigma transpose is going to give us, this is square root of 2. So sigma transpose. So you get 2d. Wait, I'm sorry, it's not lambda. It's in here, it's the matrix A. A and A transpose. It's not A transpose. So yeah, this is correct. This is A transpose. Sigma transpose. Okay. So this is 2d. And then you have to integrate. Yeah. So you have to integrate exponential a t minus s1 exponential a transpose s minus s1 ds1, because now s1 and s2 become the same. Okay. Next. Next is to calculate, so the exponential of a matrix. So if the matrix is minus lambda I plus omega j2, where j2 is equal to 0, minus 1, 1, 0. So this is your matrix. So this matrix A can be written minus lambda identity, it's clear, and plus omega out j. And j is simply 0, 0, 1, minus 1. 0, 0, 1, minus 1, right? And so, and this is, again, you can do it at home. Exponential TA is simply exponential minus lambda t cosine omega t identity plus sine omega t j2. And then if you do the, if you plug this into here, you get Ct of s is 2 sigma, you have to integrate up to s of exponential minus 2 lambda s minus t prime minus minus lambda tau. So here I did the same as before. Tau equals t minus s. And then you have your matrix multiplied by the matrix, which is cosine omega t. Basically, what you follow is the exponential of this. It's a way to calculate the exponential of this matrix. So it's cosine omega t. It should be sine omega t. And J2 is minus sine omega t cosine omega t. And you have to integrate dt to sigma minus lambda tau. And yeah, sorry, this is a tau, and tau. And so when you integrate, so this go outside the matrix. And so finally what you get when you send the limit to infinity, you get sigma divided by lambda, exponential lambda sigma. And you have your cosine, repeat the matrix, cosine omega t, sine, I'm just giving you the result, sine omega tau, cosine omega tau. And the same way, this is when you write it this way, so this is the case tau positive. You remember when tau is negative, you have to take the absolute value. And so finally, C of tau, which is the correlation function when you take t plus tau, you take the limits as t goes to infinity. And you take only the projection on x, which is only this one. You get sigma divided by lambda, exponential lambda sigma, cosine omega tau. And if tau is, this is true for tau positive and tau negative, so I have to, it's tau, absolute value of tau, and this is tau. I went fast, but this is, you can follow what I did in dimension 1 and you adjust. This is just the result of my calculations. Okay, now what is the, so I have, how do you go from here to the power spectrum for you? Which is not very, it's not very hard because you have lambda tau, cosine omega tau, and I have to multiply exponential of I omega I f tau. So if I transform cosine into the difference or the sum of two exponentials, this is what you have to do. It's not hard. So let's just write this down and look at the result. So what is the power spectrum? PSD, as we did in dimension 1, PSD is what? This is the Fourier transform of Cxx tau, so which means 1, so you integrate over r, exponential I omega tau, of what? Sigma lambda, exponential lambda tau, absolute value, multiplied by cosine omega tau. So cosine, I write it ei omega tau plus minus I omega tau divided by 2. You agree? And you integrate. So this is, I just have to be careful here. I have to differentiate r between r plus r minus. And okay, you do the calculation. You have, if you have exponential of a term which is tau, whatever it is, capital X, from 0 to infinity, it's just going to give you 1 over tau, 1 over x, right? So what is x here? It's going to give you, let's say I omega, let's call it not omega, no, sorry, let's call it f, because I have already omega is fixed. Omega is the rotation. So I have omega plus, so I have lambda plus I f plus omega. You agree? I lost it. Oh, no, it's here. Thank you. You agree with this, or I made a mistake? I take the first one. I f tau is f plus omega, and then I have a minus here. I have a minus, yeah, so with a minus. Right? And I can do the same with this. So I have a sum of the two, and it should be, so I have lambda minus I f plus omega. And now I do the same ways, 1 plus lambda minus I, and I have to f minus omega, plus sigma divided by lambda. So you go into the same denominator, you calculate, and this is what you find. Sigma, I forgot also there's a 2 pi somewhere. 1 over 2 pi. Yeah, and I have a 2 pi. Yeah, it's 2 pi f. So I forgot 2 pi, 2 pi. So in the end, you get sigma divided by 2 pi, 1 divided by lambda squared plus omega divided by omega minus 2 pi f squared plus 1 over lambda squared. Yeah, okay. So this, all right, lambda squared plus omega plus 2 pi f. I don't care about the second term, so let's ignore this one. You get, so just move to the same denominator, and I don't remember why this lambda cancels out. Yeah, because of the lambda here, I see. So the lambda, if you go, you get lambda here, get the lambda, lambda and lambda goes out. And that's why you don't have any more lambdas. Things are cancelling out. I omega minus, all right, you do the calculations, and you get this. Lambda squared plus this. What is the meaning of this? Yeah, maybe there is a plus somewhere, so that it should be like, I mean, it should be the complex conjugated here. This should be the complex conjugated of that one, so that when you multiply, everything is real. Because, yeah, I forgot, here you integrate from 0 to plus infinity, and the other one you integrate to minus infinity to 0. So you have to change. There is a plus I, this is the complex conjugated, and then you get this. What did we get? What did we get when it was pure dimension 1 Ornstein-Ulembeck process? There was no omega. Omega was 0, and we just got this with the 2. Forget about the 2 pi, this is a frequency. So it means that it decays. What it means to have omega minus this? It means that where you have a maximum for the value of f, or 2 pi f equals omega, so that this is 0. So this is the maximum. So when f equals 0, you have a number, at infinity it goes to 0, and then you have a maximum like this. And this is for 2 pi f equals omega, which is the rate of oscillation. It's our rate where the dynamical system rotates. Which means that in this oscillations, what you get? You get a mix of continuum of frequencies, because this is the power spectral density tells you what are the frequencies in this signal. So you have a mix, and most likely at you are around omega at the maximum, although there is a depth that you can estimate. The probability to have very high frequencies going to 0, but that's what you have. You have a spindle, something that oscillates with a main frequency omega, where in average, let's say, the amplitude here, as we saw before, is not zero. It varies. It can explore a range, and so you see, the potential rate is like flat here, and then it goes with a parabola. But you explore here a range which is quite flat, and this range here is such that, and you remember you have this minimum at a certain distance r0, which means in average, when you look at the 2D picture, it doesn't collapse to zero. No, the noise is able to push the system outside zero sufficiently strong, and you remember the position of this depends on the size of the noise. Okay, there are more, but the rest is more involved in terms of the calculation. For example, we have calculated what is the time to go from the moment where you are low to the moment where you are up. And we found that this time is when you repeat these calculations over all the spindles, you see, if you are in dimension 2, basically what this says is that you're not going to continue oscillating towards zero. At some point, the noise will become sufficient so that when we arrive here, the noise will push you. So you are going to oscillate in a certain region of the phase space, almost around a circle. But the circle here can collapse or can increase, can collapse and can increase. And the variation of this gives you the variation that you are seeing here. This is when you are almost zero, and then when you are increasing sufficiently large, you are going to have a radius, a distance, which is large enough.
Can we say that there is some kind of limit cycle underlying?
I don't like this much, because if you go back to the picture, there's no really a limit cycle picture that you can really use. But what I wanted you to understand is that the noise drives the system. It doesn't create oscillations. So the rhythm in the brain, according to this model, is a collection of this activity. The rhythm is a collection of this activity, which guarantee here that you can have a spectrum of frequency around omega. Okay, this doesn't collapse to zero, it doesn't go to infinity, because at infinity your system brings you back. And so you can calculate in average, that's what we did in a paper that is not published yet, in average what is the duration of this quantity and what is the time to go up. You see, the intuition is this: if you want to go up continuously, up, at some point, because of the deterministic part, this will bring you back to zero. So you cannot exceed in that direction. But once you are very small around this, the noise is going to drive you out. And the balance is what we have seen today. There's a balance between noise and deterministic behavior. Okay? So, based on this, we can just spend now a few minutes going into the PowerPoint.